In this lecture, we are going to look at some of the important lithography terms that we use in processing and qualification as well. And also we will look at how do we improve the quality and what are all the parameters that affect the quality of printing on the wafer. So, the first term is exposure latitude. So, what do we mean by exposure latitude? So, exposure latitude is a measure of patterning quality of the illumination and resist process put together, right. So, it qualifies both illumination and resist process together. So, what we mean by that is we are measuring the line width of your photoresist after patterning, right. So, we have developed and we have gotten this photoresist pattern, and then we are measuring the dimension of this pattern, and then we are qualifying how good exposure stability is, right. So, just to give you an example, on the left side you see a graph that shows two lines, one is green, the other one is brown, right. So, let us look at the green line, right, and then the x axis is the illuminating dose. So, when I increase the dose, the line width reduces, right. This is something we also saw earlier. So, in this case, just to recall, you have an opaque region and then you have illuminating region at the side. So, this is a positive photoresist. So, whatever you illuminate will be washed away, right, and this is what your photoresist will look like. So, when I increase the dose, right, when I increase the dose, what happens? The line width reduces, right. So, the line width is going to shrink. So, that is what we see. And then there is another process that has a steeper slope, the blue one, right. So, now I have a target, right, I have a target line width, a certain line width, we call the critical dimension, and then I want to see how much is my variation in my critical dimension if I change my exposure, in this case plus or minus 5%, right. So, E naught is the target dose that will give me the actual target, right. So, E naught is the optimal dose, and then I would like to see if I change my exposure dose plus or minus 5%, how my critical dimension is going to vary. So, this is very natural to expect, because when you are illuminating, it is very hard to expect that your illumination will always be constant, right. There could be some fluctuation in the illuminating dose. So, that is one cause. The other cause could be your wafer itself. So, if the wafer is not flat, if your focus is not proper, you will also see some change in the energy that reaches the surface, right. So, you want to understand if there is a change in the exposure dose, how my critical dimension is going to change, and this can be characterized by exposure latitude percentage, right. So, a change in the exposure dose and how much change I get in the critical dimension, right. So, this actually enables you to qualify the robustness of the process toward dose variation and thickness variation as well, because your dose changes as a function of thickness of photoresist. If the photoresist is thick, you need more energy. If the photoresist is thin, you need less energy, right. But you will always have some thickness variation across the wafer when you coat your photoresist. So, you want to know how robust your dose variation is to your thickness, right, and reflection issues as well, right. This is something we saw earlier. So, when the light comes down and then when hits it, so there will be also some reflection. So, if the reflected light also exposes the photoresist, that is something that we should also take into account, and this exposure latitude will help you to understand how well you can control it. You always want higher exposure latitude. So, you want the latitude to be larger so that your process is very robust. And then the next thing is about depth of focus, right. We saw this depth of focus in our imaging lectures, right. So how your focus affects your image, right, and what is the origin of this depth of focus and so on, right. In this case, what happens if you change or if the depth of focus changes, right. Let's take an isolated line. So again, I'm taking an isolated line and it has a certain critical dimension, right. Now I'm changing the focus, right. What I mean by that is you have this focal length and then this is what you have. I'm going to change the focus. So this focus could be coming from your wafer location. So if it is not at the optimal location, it's going to go up and down, right. So this is how your rays are going to look. At the optimal focus, you get the best image, right. This is similar to the picture that we take with your camera, if you remember, right. So I'm going to move this focal plane up and down, right. So what happens is your critical dimension will also change, right. So your critical dimension is also changing because of non-optimal focus, right. And this is what we capture in this exposure dose and variation picture, right. So your depth of focus is measured by varying your focus onto the wafer and measuring the target CD. So if I change the focus, obviously there is a change in the dimension, right. So let me draw this here. So I get something like this for an isolated line, right. IL is the isolated line for a certain energy E, right, and this is your CD and this is my depth of focus. So obviously there is a target that I reach, but then if I change my depth of focus, my CD changes, right. But then my dose will also vary, right. We saw in the exposure latitude. So what happens if I change my dose? So if I reduce my dose, your CD is going to increase. So this is E minus delta E, right. And then now if I reduce it, this by using higher dose, E plus delta E, okay. So now if you take this best depth of focus, all these points, let me pick a different color. If I pick all these points, what you actually get is nothing but your exposure latitude image, right, that we saw, right. But then if I explore all the possible depth of focus, this is at a certain depth of focus. So now I'm changing the depth of focus. I get this group of plots, right. So this variation in both exposure dose and depth of focus is called boson curve, right. So you change both energy and also depth of focus, and this is what we call dose exposure focus or exposure matrix, and this is called boson curve, right. And you get this kind of set of individual plots. So what is the interest in generating this kind of plot is the question here. So here we are looking at the process window. What is the acceptable range of dimension for the designer? So when you design something, you design for a certain dimension and then you give a certain percentage variation. When you design a device or a circuit, you say, see, if my critical dimension variation is within 5% or within 1%, my device would work properly, right, as desired. Or if my variation is within 5%, my circuit will still yield what I actually intend to do, right. So you want to look at what is the window of exposure dose and your depth of focus within which you will get this desired variation, right? And this is what it will be, right? So let's say my plus minus 5%, right, is within this window, and then I can draw this line, right? And then I will draw this line, and then that line will give me an intersection within this all these curves. I'm going to mark those interesting points here, right? So these are all the interesting points, right? So within the specification of the designer, and within this particular window, right, within this particular window, I am within my required specification. So I don't have to worry about the exact depth of focus or exact exposure dose. My dose can vary within this range, and my depth of focus or the focal point, right? So here we had this focal point. My focal point can vary within this region. And this is what makes lithography, the projection lithography, very robust. You see pretty large windows, right, that you get. And this can be, in the order of few tens or hundreds of nanometers, right, the window can be. And this can be, the exposure dose can be 5 to 10% variation, which in commercial systems are pretty tight, but your depth of focus is controlled by your wafer flatness and so on, right, that we saw earlier. So you create these kind of focus exposure matrix, in the other words Boson curve, so that you can qualify your process window. And this becomes a very essential part in lithography process optimization. Okay, this only applies to projection lithography system. In contact lithography system, you don't have this problem of depth of focus. The reason for that is both your mask and your wafer are in contact, right? There is no issue of depth of focus or focal point. Okay, and the nature of the curve will vary, right? So here we saw a downward looking curve, and on the top for the grating you look upward looking graph, right? So this depends on whether you are looking at a line or a trench, right? So if it is a dense pattern, if you are looking at this trench, or whether you are looking at this line, based on what you are actually measuring, your nature of the curve can be different. But nonetheless, the investigation to look at this process window, right, this is what called process window, is going to be the same, right? And the next thing is the linearity, right? So what is linearity? So we want to have one-to-one mapping of the dimension between mask and photoresist, right? So if the mask dimension is some x, right? Of course, this is taking into account the magnification factor, okay? And on the mask you want to also, on the wafer also, you want to have the same dimension. So this is what we call linearity. So you could have varied dimension on the mask on your design, right? So one structure might be 100 nanometer, and then it can be, there are multiple devices, and then one could be 1000 nanometer, right? So you can go from 100 nanometer to a micron, but you want all these structure to yield to accuracy, right? So that your circuits are performing the way you want, or your devices are working the way you want. So how do we ensure that all these devices yield? So in order to do that, you want to look at the linearity of this particular process. So normally this is done through metrology. So you will take different dimension and see, this is what I had on the mask, and what do I get on the photoresist, right? So if you do this mapping, I want it to be very linear, right? So the linearity qualifies the process is good for varying dimension, okay? And the next thing is proximity effect. right? Proximity effect is an undesirable occurrence in this whole imaging system, right? So the dimension of the feature is affected by presence of features adjacent to your desired feature, right? So if the dimension of my desired device is or feature is affected by the neighboring feature, we call it as proximity effect, right? Proximity of any other features to my feature, right? And this depends on the distance between the feature, right? That is one thing. And the other thing is the wavelength of the light that I am using as well, right? So these are all the things that determines the degree of this proximity effect. And this proximity effect could bring in CD variation with respect to pitch, right? So what is pitch here? So if I have line space structure, the distance between two consecutive lines or space is what we call pitch, right? So as I mentioned, if I reduce the pitch, my neighboring device is coming closer, or neighboring feature is coming close to my line here, right? They are closely spaced, and this will have an effect on the trench width or the line width. Line end shortening, we will see that in a bit. That is also an undesirable factor because of proximity. Corner rounding is also an issue because of proximity. Let us look at these things a little bit more carefully. So let us look at how these proximity effect affect the structures. So this is a simple example of a dense and isolated feature in one device or one structure, let's say, right? So you have a same CD running across this line as a same CD, but the only difference is the environment change, right? So here we have on the top we have a dense feature, so you have other features coming close to the line of interest, but then at the bottom side you can see it's free, so there is no structures coming close to the device, right? So when we print this, we will find out that the dimension of the central line is not uniform, right? So it's going to have a CD variation. So the critical dimension or the line width is going to be different. So let's understand how this is going to work, right? So we have a dense feature on the top. So what that means, the light that is coming through, right, so is going to be taken out. So the light, let's say this is all opaque, right? So if it is all opaque, the amount of light that is going to come through the top end is going to be very less, right? And also it is going to be affected by these two features. So if I have to draw the aerial image on top, then it will be better for you to understand. So on the surface of the photoresist, you will find an image like this, right? So this is what the intensity pattern is going to look like. So as you can see here, you are very close to this edge, right? So your presence of the two lines, right, adjacent to the central line is actually pulling the power down here. That means your patterns will be slightly narrower in feature. But then if you take the isolated line, you will have a feature like this, right? So there is a lot of light coming through it from this side, right? That will make it pretty broad, okay? So when I look at this whole structure, at the top end your line width is going to be narrow, right? At the bottom side your line width is going to be broad, okay? So this is how you will find the effect of proximity effect. So there are multiple ways to address this proximity effect, called adding assist features and so on. We will see that in a bit. So now we will look at what is the effect of proximity first. And on the right side we have something called line end shortening, okay? This is line end shortening, right? So in this case I have a line, right, that terminates here, but I have a perpendicular feature, right, coming close to this line. Okay. So, I have a certain distance between these two. So, when I print this image, what I will get is a shortened line. So, instead of having your edge close to this, my line edge will be much smaller. So, the reason for that again here is, you do not have sufficient distance between these two, and inefficiency in getting light through this system makes this line shorten, right. And then the next thing is about corner rounding, right. So, on the left side you see the mask pattern, right. This is what a designer had designed, right, with very sharp corners, right. But then when you print it, you see a rounded edge, right. This is the pattern on the image. So, the reason for this is resolution basically, right. So, let's understand what is the resolution limit here. So, we say resolution limit is nothing but how small a feature can be printed, right. So, in this case this is your critical dimension. So, let's look at this corners little bit carefully, right. So, if I look at the dimension, right, this is your critical dimension. So, as I move closer and closer, my dimension is reducing, right, and at this point you are almost going to 0 nanometers or so, right. So, if my resolution is let us say a certain x nanometer, I will be able to image only to that x nanometers. So, below this I will not be able to reproduce that image at all, right. So, whatever features I have below this, I will not be able to reproduce. The same thing applies to this edge as well. Okay. So, the distance between this, right. So, in this case it is the line, right, and this case it is trench. Again the same thing applies, and then you will not be able to reproduce that corners, right. And if you are a signal processing person or image processing person, you would know that these sharp corners have got high frequency, right. The sharp corners can be only reproduced if you have large number of coefficients, right. In the Fourier series you need large number of coefficients to reproduce this. In other words, you need more number of diffraction orders in order to reproduce these sharp corners, right. This is again the resolution limit. And this is an example of how to improve your resolution, right. And proximity effect is a classic example of this resolution enhancement. On the left side you see 180 nanometer technology and 248 nanometer illuminating optics, right. So, this is what we use, and the structure on left and right are exactly the same. Okay. We are illuminating exactly the same object, and your bulk holes, right, that means the holes that are inside got a hole diameter of 420 nanometer, and the edge holes got only 380 nanometers. This is a classic proximity effect, right, the edge effects. But then I am imaging the same structure by using 193 nanometer illuminating optics and laser, and using 130 nanometer node technology, right. So, when I do that, the bulk and the periphery, right, the edge holes, the difference is only 4 nanometer, right. In this case it is about 40 nanometer. So, look at the reduction in the the non-uniformity you get. So, this is the reason why going to higher resolution, right, or reducing the wavelength will help you in tackling this proximity problem. And the other thing to circumvent this proximity issue is by using assist features, right. So, we saw this L shape, right, earlier on, that was giving us some rounded, right, corner rounding. So, this is a simulation image. On the left side we see without OPC, right, what we call optical proximity correction, right. So OPC is optical proximity correction, that's called OPC, right. So if you don't do any optical proximity correction, you get two things. One is line and shortening, the other thing is the corner rounding. So how do we handle this? The way to handle this is by adding assist features, what we call sub resolution assist features. And here, since your lines are getting shortened, we use this assist features to extend the line, right. So what we can do is we add these kind of sub resolution assist features in order to pull the light out. Similarly, in this corner you are getting structure outside your area of interest, right. So what you do is you push it in, that means we remove that particular area, right. There is no structure in that area, and then we add a structure outside this. So this is how you profile your structure in order to get an optimal image, okay. So this is an assist feature, but we call it a sub resolution. The reason for that is it is present in the mask. This is at mask level. It is present in the mask but not present in the image. So in the image, if you don't want anything in the mask to be reproduced on the image, you want to make it sub resolution. That means it is below the resolution of the imaging optics, okay. And on the right side, it's a very good demonstration of how to convert, right, a simple binary pattern by using all the assist features and then reproduce what you want. As you can see here, this is a complex structure to actually enhance this proximity effect, right. So whatever you are printed is completely different from what you want. If you want a two isolated features here, what you get is a complete blob, right. It's not at all resembling what you wanted. But then at the mask level you start adding assist features, right. This is sub resolution assist features. What you get is a reasonable reproduction, okay. But now I am going to take this to a different level by profiling the optics. So now you see the assist features are all over the place, right. And then when I do that, the image is very close to what I wanted from the binary image that I had here, right. So this is how you create nearly perfect reproduction of the image by using sub resolution assist features, right. Actually this should be surf, okay. And how do we do this? This is very difficult to do experimentally, right, because each time you cannot make new mask for all the assist features. So this is all computationally done. That is called computational lithography, where we image this using computational tools and then we feed back the information to the mask design so that we can get reasonably good reproduction of this image, okay. And this is the process flow to reproduce that mask. So you start with a layout, right. This is coming from your design, and then you do DRC. What is DRC? Design rule check. So design rule check. So they check all the design rules are followed or not. For instance, if my lithography limit is only 50 nanometers, and then in your layout or in your circuit if you are asking for 50 nanometer, it is a violation because it cannot be reproduced. So this design rule check makes sure that whatever you design can be reproduced in your wafer. So that is the first step, and once it clears that design rule check, when it goes for manufacturing, we do a pre-OPC, right, optical proximity correction. So first we image it and then see whether we need to do some assist features or not, right. The sub resolution assist features need to be added or not. So if it is needed, we add this, we do a waveform expansion. This is all the optic simulation that we do, and then we also look at how much assist feature need to be added, because that adds cost to the system. And then we do some simplification of this assist features, because you may not need all the features, because when you put it through a wavefront expander, that algorithm is going to add whatever possible in order to make the image perfect. So you do some kind of smoothing and so on, and then we do the proximity correction, and then this is optical rule check that we do. This is after adding all these assist features, and then it goes for mask making, right? So these are all the steps involved even before the mask making that we saw earlier. Okay, so this summarizes the process flow in mask making, and that brings us to the end of this lecture on the different type of mask terms that we use to qualify the process, and also finally looked at how do we increase the resolution or avoid proximity effect in this lithography system, right? So with this, we have a very detailed understanding of the mask technology, what are all the important terms that is used in mask processing and also litho processing. And now we need to look at how do we increase the resolution of the system, right? So one way to increase the resolution is by assist features, right, by avoiding this proximity effect. But that is more of adjustment that you do to reproduce the image. For instance, you have 100 nanometer lines, and then in the next technology node you want to reduce that dimension to 50 nanometer. So how do you do that? So what are all the ways to achieve a better resolution with lithography is going to be the follow-up lecture